All right. So, new chapter, right? New chapter completely. The ideas from forces will play a small role in this topic. So understanding the concept of the force applied at an angle, the idea of what a force physically is will come up, but it is a new topic. It is a brand new idea. So if you did really well in the last topic, that's great, but you got to make sure that you're focusing here on a new topic. If you struggle with the last topic, let it go. All right, get it out of your mind and think about this as a new idea. I personally think that work and energy is one of the easier topics in the year, easier than forces. And I'm not just saying that to you guys, I'm not lying. A lot of you notice, I think, that forces were a little bit easier than what we did in the previous quarter. This is, again, a topic that's not as difficult, I don't think. It takes practice, though. It takes practice to do well in these topics, like all other things. So we're going to start with the concept of work. The whole chapter is going to be about energy. Now, when we think of energy as you're running, you're expending energy. You're eating food, you're gaining energy, right? You think of when you eat something, you gain mass. So you gain energy also. When you look at the food label, on the back you see the amount of calories in an item, right? Calories are a measurement of energy. Calories measure energy. So when you eat a piece of food that has a certain amount of calories in it, you're getting a certain amount of energy. Now, some of that energy is good energy and some is bad, depending on the saturated fats and different things, right? So we know that just the number of calories is not indicative enough of what the actual food is made out of, but the actual consistency of it too. But calories, the amount of energy that we gain from it, are then expended by our physical actions throughout the day. So we're going to start with the concept of work. We're going to begin this idea of what's called scientific work, or physical work, not work that we consider just a word work, but scientific definition of it. We'll talk about when work is actually being performed, and then we'll talk about the concept of net work, or overall work. Okay. So here's our first definition of work. So the work done is the product of the component of the force along the direction of displacement. So simply put, we're looking at F times D times cosine theta. So let me explain where this cosine theta comes into play. So if I have an object, and let's call it for now a sled or a crate, and an applied force is being acted on this at some angle theta, the assumption here is that the direction of motion is to the right. So again, we're looking at the force applied at a given angle theta, but the direction of motion is between the angle theta is between the direction of motion and the force itself, right here, sweeping out that angle. So in this problem, motion would be to the right. So it might be useful to start labeling the direction of motion in these problems. Now, free body diagrams are not going to be as needed as they are in the previous chapter, but once in a while we'll see where they do come into play a role, especially when we talk about friction and such. Now, I could take the exact same setup, with the exact same force, and I could say, what if the motion is upward? Well, then the angle theta would be here. So for all work problems, it's going to be the applied force, or whatever force is doing work. We can have friction do work also. The force itself times the distance traveled times the cosine of the angle between those things. So this one is an easy one to see example, right? Like this is obvious. You pull on a sled or a crate or something attached to a rope and it pulls behind. Think of a pickup truck that's pulling a car that's broken down. There's usually a cable attached to the car lifts up to the front, and the tow truck pulls the car behind it. So that's an easy one to see an example of. How about this one now? When would there be an object being pulled at an angle and yet it moves upward? Where could that come into play, Joe?
Like a helicopter is lifting something up.
Okay, a helicopter, good. What else? A ramp, good. And anything that involves some sort of angled force where the object slides up and down. The one that I think about is like that traditional, I think we called it a coal mine or a coal shaft, where you're lifting something out of the ground. So imagine that this is the object itself. The object itself, let's say that, erase this a little bit, here we go. So that this is the corner itself. And let's say that there's a little pulley here. And there's a force applied, right? There's a force applied here that gets transmitted to this cable, so there's tension in the cable. And this object is going to be moving upward. We say it got lifted out of the ground like that. So the motion could be upward, while the angle itself now is between here and here. So the key to this problem, or to any work calculation problem, is to recognize that theta is the important part. Knowing where theta is. And again, theta is the angle. Maybe you want to jot this down in words, right? Theta is the angle between the force and the direction of motion. Theta is the angle between the force and the direction of motion. So we don't have to worry anymore about sine versus cosine. Which one should we use? Is it the x component? Is it the y component? For this topic of work, as long as you know that theta is the angle between the force and the direction of motion, we're always going to use FD cosine theta. Now, units-wise, if you take a look at the units bolded there, we know that the units of force are newtons, and the units of distance are meters. So those are my units there, right? Newtons times meter. And that happens to be a new unit. We're going to call it Joule. It's our unit of energy. It's synonymous to calorie, like inches and centimeters, joules and calories. So they're both units of energy, but one is the SI system and one is the English system. Just like inches is the English system, and then we say centimeters would be like the SI, or meters in that case generally. So joules are just another way of saying the word calorie, but a different value. Okay, joules are like calories, they're energy measurements. What energy measurements do we use for like air conditioners or heating systems? Watts are power, actually. We're going to get to that in section 6.4. Watts are related to this, but that has to do with power. Degrees? Not degrees. We measure the temperature itself in degrees for sure, but what are the energy measurement units that we use? Has anyone, it's one that people don't always hear of. It's not volts. Voltage has to do with the amount of electricity supplied, but the actual energy being consumed by the actual air conditioner heating unit. It's called BTUs, British Thermal Units, BTUs. It's a very applicable one. That's why I mentioned it, so you understand where you're going to use it. Now, BTUs, again, like calories, like joules, are just another measurement of energy. Okay, just a measurement of energy. It's a British thermal unit. It was started in Britain, in England, right? So BTUs are used a lot when you go to purchase an air conditioner or a heating unit. You'll see the rating in BTUs. So I want you to be familiar with that. That has to do with the amount of energy that's actually giving off. But we're going to be focusing on joules. Okay, we're going to be focusing on joules. So that's going to be our unit. So a joule is really comprised of Newton times a meter. That's what Newton times meter becomes. It becomes the unit of joule. Just like the unit of Newton. Anybody remember what the unit of Newton was? Newton was comprised of several other smaller units. Like when I talk about forces, and I say 37 newtons is the force applied, what was Newton really? This is one of the most don't remember always. Think about F equals ma. F is newtons, ma is the other side. They have to be the same unit. So m times a is kilogram, m is kilogram, a is acceleration, that's meters per second squared. So a Newton, if we think back, a Newton was a kilogram meter per second squared, which was comprised of that whole thing. Now we're taking newtons times meter and making a whole other unit out of it called the joule. Okay, called the joule. When we get to energy, we talk about potential energy and kinetic energy, things that you may have heard about, those terms in your 7th through 8th grade science courses. You might have heard of potential and kinetic energy. We'll use the same units of joules. Okay, we use the exact same unit. So energy is going to be one unit the entire chapter, and that unit will be joules. Keep that in the back of your mind. All right, let's take a quick look at an example of this, and we'll get into something a little bit trickier. How much work is done on a shopping cart? Done on the shopping cart when it's pulled 12 meters by a force of 75 newtons at an angle of 60 degrees. At an angle of 60 degrees. Now, if you're not given the diagram and you're told it's pulled at an angle, the assumption we have to make here is that this object, shopping cart in this case, here's my applied force, has an angle between it and the direction of motion. So I don't really need a free body diagram as much anymore. I'm drawing a diagram here to show you what's happening, but I'm not drawing the weight pulling down and the normal force pushing up. If I have friction involved in the problem, then I probably need the y direction. because remember friction involves Fn, and Fn is in my y direction. Remember, normal force for these problems where it's flat on the surface, normal force is in the y direction. So when we think about these kinds of problems, we have to consider when friction is involved, it does make sense to draw the full free body. But for now, I'm only trying to find the work done by this applied force. And if I think about my formula for work, it's force times distance times cosine theta. Now, the work done is by the applied force, so I might call it Fa. Okay, the general formula is there, but I'm giving a specific subscript here. It's important to give it a subscript because later, what if you're pulling on the object and there's friction? Then F could be FF or it could be FA. Again, if I'm pulling on an object but friction is also present, then the work done could be the work done by my applied force or the work done by friction. So it's important to give a subscript for the force that we're actually analyzing or utilizing in the problem. So this is my setup here, and I just have givens. This is just a straight plug and chug problem. The applied force was 75 newtons. The distance the car traveled was 12 meters. And the angle here was 60 degrees. Again, it doesn't give me a diagram. We're told that the 75 Newton force is applied at an angle of 60 degrees. We have to assume that angle is with respect to the direction of motion. We have to assume that that's the angle. Now, if it says the object is moving vertically, then it's different, right? Then we start to consider the angle being this angle here. Okay, right there. But think about a shopping cart, right? Think about a shopping cart. If you pull on a shopping cart, so by the way, when do you pull on a shopping cart? Usually you push, right? But when do you pull on a shopping cart? When you're backing up, good example. When else? I wasn't even thinking about that, Helen. Good. When you're backing up.
When you're like taking it out.
When you're taking it out of the actual thing where there's like they're all stacked up, also a good idea. When you're turning, you can still push it though. Have you ever seen like, you know, when you have like when you're a kid and your parents are all shopping together and you want to like pull on the cart from the front? So although it says pull and you think push for shopping cart, it says pull in front. So maybe this is the shopping cart and like your parents are pushing the main component, but you're on the end pulling it. Or you can literally see somebody pulling it. But as you guys said, the better example I think is when you're backing out of that little container, right, where they're all stored, or if you're just literally backing up to let someone through maybe. So either way you're pulling on it or pushing, it doesn't make a difference. But think about a shopping cart. Which way does a shopping cart move? Horizontally or vertically? I hope horizontally, unless you've ever seen Trailer Park Boys? You hear that show before? Or no? It's kind of a ridiculous show, but one of the characters likes to, I think, gather shopping carts. I saw like a meme of it the other day. Anyway, whatever. So I was going to say was they used to have to throw shopping carts like over like a ledge or a cliff. So unless you're doing something crazy like that, a shopping cart moves horizontally. So we know motion is left to right. So what do we get as a value for the amount of work done? 450. And my units are joules. Okay, that's the amount of energy expended by this person. Now, what if this person went twice as far? What would the answer be? 900. Good. Because distance is right here, and is directly related to the work done. So if I double the distance and go twice as far, my answer is going to be twice as much. Agreed? What if I double the force? I'll also get double the answer, right? So both of those are directly related. So the more force I apply, and the more distance is traveled for, the more work is done. And that's logical. Think about it. For those that think about like, physical fitness, if you watch football players have to actually run into like a, what do they call that? Sled? They call it a sled. It's not really a sled. It's these posts with these dummies, right? With these cushions. And the football players will run into it and push it downfield. That's literally exactly this. The further you push it, doesn't it take more energy for you? For those that are into physical fitness, the further you run, it takes more energy. The further you, lift an object, maybe you're doing a power clean, you only go to here versus you go here, and then you go all the way up above your head, that's going to physically take more energy to do it. Because more distance in that case. Now, if suddenly, today you're lifting 100 pounds, and then tomorrow you lift 120 pounds, that's increasing the force, right? So that's also going to cause more work to be done. So you can see how these are both directly related. What if I apply a force right now, ready? Force applied. I'm doing it. Nothing moves. How much work did I do? Good. Good, Nick. Why 0? Yeah, D is 0. Think about that for a second. I can apply all the force in the world to this desk, but if it doesn't move, I'm not doing any work by definition. The scientific definition of work, force applied over a given distance. It's got to be over a given distance. Without distance, this becomes 0, and 0 times anything is 0. Okay, so it's important to recognize that if you're not physically moving something. So for those thinking about weightlifting or that concept, it's a very easy one to think about. You lift a dumbbell, right? Let's say you're doing a power clean, right? You lift it up here, you come to here, and then you lift over your head. And you hold the weight here for a little bit. Lifting it up, you're doing work. But believe it or not, while you're holding it here, you're not doing any work. It takes effort, for sure, I know that. So you're thinking right now, like, that's ridiculous. Obviously, it's taking energy to hold like 200 pounds above your head. That takes physical energy that you're giving. But it's not actually doing any work while it's not moving. Now, when you start to lower that weight back down, you're still applying a force upward, but you're lowering it over a given distance, then you're doing work. But while you're holding something physically above your head, you're doing 0 work. Okay, 0 work to hold it there. Getting it there, you are doing work though. So how about the second question? This is more conceptual. What would the angle theta be if the force applied is a horizontal force in the direction of displacement? In the direction of displacement. So what kind of example am I giving now? Well, let's say we had, I don't know, I need a bigger container here. I'll use this as an example. I'll use it back here so it'll turn low. So let's say the garbage can is here, okay? And I apply a horizontal force to it, and I'm pushing this way. That's why I put it on the desk so you can see. Applying a horizontal force, it moves this way. What's the angle theta going to be in that circumstance? Ellen, what do you think? 90 degrees?
Or 180 since it'd be a straight line, but 90 because like the angle you're making with your arms is that actually what everything is.
Okay, I can see that. It's not 90 in this case. 180 is closer, but it's not 180. But you're on the right track. It'll be 0 actually? Yeah, it's one of those 3, right? You can tell it's at the 90. So let's think about this for a second. Here's the object. Okay? Let's draw the applied force. It's a horizontally applied force. And it's in the direction of displacement, which means motion. I'll draw in red here. Motion is exactly in the same direction. So the only time there's an angle is if there's a little gap between motion and FA, right?
180 is the opposite direction.
Yeah, what's going to be 180? What's going to be 180 in the opposite direction physically, though? What force is going to always be 180?
Friction.
Friction. Think about what Helen just said. She made a lot of good connections there. If I push on this object that way, which way is friction pushing? Which way is friction pushing? The opposite direction, right? So friction, it turns out, is always at an angle of 180. Let's jot that down. Really important. Okay, so if I apply a force horizontally and the motion is horizontal, this example, theta equals 0 degrees. But if I apply a force to the right, or so let's say the object is just sliding to the right and suddenly friction acts on it. Well, friction is going to act this way, while motion is still to the right. And in that second case now, the angle theta is 180 degrees. So it's important to recognize, and maybe you can consider this as a thing for the rest of the chapter, the force of friction is always at an angle of 180 compared to motion. And we're talking about sliding friction, not rolling friction, okay, not with a wheel. We're not concerned with rolling friction right now, but sliding friction, or what we call kinetic friction. It's always going to be an angle of 180. And where's that angle? Take a look right here. For those that aren't seeing it, that's 180, right? That's 180 degrees right there. This is 0 degrees. You're not moving at all. Literally 0. What about 90 degrees? What about 90 degrees?
That'd be like those degrees directly vertical.
But then you'd be pulling up and it'd be moving up.
Yeah.
So that'd still be 0 degrees. But let's discuss that. I like that you said that though, Nick. Let's discuss that first before I go on to 90. So if I had an object that was being pulled upward and it were moving upward, that angle is still 0 degrees. That's still an angle of 0 degrees between motion and the applied force. So unfortunately, if it's pulled upward and it moves upward, it's not 90.
If the motion is horizontal, but then the force is vertical.
Yeah, if somehow the motion is horizontal, but the applied force is vertical. So, for example, right? Take a look at the eraser. I'm applying force to the right. It's moving to the right, so my angle is 0 degrees. Which way is gravity acting on this object? But I'm moving it to the right. So if I'm moving it to the right and gravity is acting down, it must not be doing any work. So, no. You're wrong. So if gravity acts down, did I sound good? Okay, hold on. I'm trying to prepare. So if gravity pulls downward and yet the object is moving to the right, gravity is doing no work on the object. But, if I just drop this eraser, which way is motion right there? And which way is gravity pulling? So the angle between gravity and motion when I drop something is 0 degrees. So when you drop an object, gravity does work to pull it down. It applies a force of gravity over whatever this distance is. So we can find the work done by gravity when an object falls down. But when an object is pushed to the right, gravity pushing down, pulling down, it does nothing to it. It does no work. The normal force pushing back up does no work either. Only the forces acting in some direction of motion do work on the object.
I don't understand why gravity does no work on the object, even if it's moving.
Because which way is it moving?
It's moving to the right, but
And which way does gravity act?
down, but isn't gravity holding it down?
So gravity is like affecting it to keep it there for sure. But remember, the definition of doing work is a
So it's
force
moving
applied
direction.
over a given distance.
Yeah.
And since that force is down, it would have to be moving somewhat down for gravity to do some work. Now, it could be at an angle, like the inclined plane, like you guys did in the first quarter. And if the object is sliding down the inclined plane, then it's moving at an angle, so it's partially moving down. So in that case, gravity is doing some work if it's at an angle. But if it's moving completely horizontally and gravity is completely vertical, that's an angle of 90 degrees. And if I go back to my definition real quick, and I write this down, whenever the angle is 90 degrees, this becomes cosine of 90, and the cosine of 90 is 0. God bless you. So the work done for any problem where the angle is 90 degrees is always going to be 0. Okay, because the cosine of 90 degrees is 0. How about the cosine of 0? What's that? Tell me your calculator if you happen to know it. What's the cosine of 0 degrees? 1. Think about that for a second. The reason this is a 1, if I plug it into this formula right here, this becomes a 1, so it doesn't have any effect on the answer, right? So the work done by a horizontal force on an object moving horizontally is just the product of F times D. This becomes cosine of 0, which is 1. It doesn't affect the problem. But if I have 90 degrees, it goes to 0. What about this one? Cosine of 180. Negative 1. What force is applied at an angle of 180 degrees? What did we say? And friction would do what kind of work then? What kind of work you said? Yeah, in general, not positive, but negative work.
Negative.
Friction does negative work. Therefore, or that's why, the angle is 180. Friction physically does negative work on an object. When you push an object to accelerate it, you do positive work on said object. Okay, so depending upon which direction your applied force is, or your force is here, it's going to affect our answer for sure. All right, let's look at a couple of visuals of this. So all we're seeing here is two different examples, one with negative work, one with positive work. Let's start with the negative work. In the first case, this little spring car, these cars are the ones you pull back on the wheels and let go. In this case, it's just a little spring mechanism at the top. So you store some energy in the spring, right? You let go of it, it's going to start to move to the right. But if you're pulling back on the object and it's moving right, you're pulling back, it's moving right, you're going to be doing some sort of negative work. And the idea is that, look at the angle here. This is the angle. That's the entire angle. That's the applied force. That's the direction of motion, that big angle there. So give me a sample angle between, this is 90, right? This is 90 here. So this is clearly more than 90. That's fine. 120. Type in cosine 120. This is where calculator's going to help you, right? Type in cosine 120. What do you get? Negative 0.5. Type in cosine 91.
-0.17.
Type in cosine 179. I'm purposely picking these numbers.
Oh, everything that's past 90.
Everything from 90 degrees to 180 degrees for the cosine function is a negative answer. By the way, if you're not getting the answers that we're saying, you might be in radian mode instead of degree mode. So make sure your mode is under degree. So anything that is an angle more than 90 up until 180 in that domain gives you a cosine function that responds negatively. Because you're doing what kind of work? Negative work. You're impeding the motion. Right? You're stopping the motion of this car. Same thing here. Take a look at this one here. You're clearly stopping the motion of the car as well. Now, this one is a little bit less obvious because of the way it looks. But think about logically in your mind. This hand is resisting motion. So if I think about like a football. Football is such an easy sport to use. I keep using it, sorry, but it really is with forces and energy. So think about a running back running with the ball. A linebacker going to tackle the running back is doing negative work on the running back. Logically, they're slowing that person down. So if a running back is running toward me, I'd have to push in the opposing direction to stop him or her from running. So I'd have to be doing negative work. That's this example right here. It's more obvious than this one is. Right? I'm pushing that way, and yet the object is pushing or going this way. That's an example of negative work. Negative work. The reason this looks confusing is because a lot of students think that this is the angle theta here. And let me discuss this. See this force here? It looks, or people think that that's the angle. In reality, the direction of motion, and I'm going to draw it in, I guess I'll use blue, I'll try to. The direction of motion from that applied force is this way. That's the direction of motion right there. Forget this one on the right. So just look at this. That's the applied force. That's the direction of motion. So look at this angle. This angle, again, is more than 90 degrees. This is the angle theta right here for that example, whereas this was the angle theta right here. That's the direction of motion right there. So if you want to draw in your angles to show so later on you recognize that theta or that's theta, again, for this example. We'll get to this one in a moment because that's going to be the angle theta for that second part. Positive work means that instead of impeding motion, what are you doing? Instead of impeding motion, what are you doing there? Yeah, you're aiding or helping the motion of the object. So in these cases on the far right, direction of motion is given there. There's my angle theta. In this case, direction of motion is given there. There's my angle theta. So look at the diagrams on the right. You can see that both of those angle thetas are not greater than 90. Both of the angle thetas on the right are going to be less than 90 degrees. And try the cosine of any angle less than 90, it's going to be positive. And I should say between 0 and 90. Between 0 and 90. You're going to learn a lot about cosine and sine and when they're positive and when they're negative in the third and fourth quarter of your Algebra 2 trig course. So unfortunately we're learning a little bit earlier, but if anything it'll probably help you in your math course to recognize these values. But you don't have to memorize them. You have a calculator in this test. In your math class, when you get to this topic, you need to know these ideas. And you'll see how they come up and play a role, and you may not be using a calculator. You may, I don't know, it depends on the test. But the idea I want you to get is that when the angle is less than 90, you're going to have positive work. When the angle is more than 90, you have negative work. That's a simple thing you can jot down, right? How would I write that as an inequality? I might just say when theta is less than or equal to, or no, I should say less than 90 degrees, we have positive work. When theta is more than 90 degrees, we have negative work. That's a quick shorthand way to write that down. Now, yes, theta is between 0 and 90 technically, isn't it? And here theta is technically between, here theta is technically between 90 and 180. So how would I write that actually? Let's draw this the way that it would say. It would say, in set notation, it would be between 90 and 180 degrees for that one. And here it's between 0 and 90. So I can give a range of value here from 0 up to 90, and then from 90 up to 180. Those are the circumstances that occur. Remembering that I didn't use a less than or equal to sign anywhere. Notice that? Because if it's at 90 exactly, If it's at 90 exactly, how much work are we doing? 0 work. Okay, so I can use a less than or equal to sign with the 0 and with the 180, but not with the 190, not with the 90. If I'm exactly 180 degrees, cosine of 180 is -1. If I'm at exactly 0 degrees, the cosine of 0 is +1. So those work, but I cannot be at 90 degrees and have the statement true. When I'm at 90 degrees, the work done is equal to 0. Okay, there's 0 work done when theta is at 90 degrees. So those are my 3 cases right there. Okay, when it's between 0 and 90, when it's between 90 and 180, and then when it's exactly at 90 degrees, the kind of work we do. So let's look at a problem for today to get an idea of how this could be applied. So now we're going to get into the real problem. Not just an object being pulled, but an object moving due to an applied force, but also under the influence of friction. So in this case, a student pushes a 20 Newton desk with a horizontal force, a horizontal force of 12 newtons, a distance of 24 meters. Assume in this problem that the coefficient of friction, kinetic this case, between the desk and the floor is 0.2. Okay, what is that, by the way? Coefficient of kinetic friction. What variable is that again? Elias, what are you thinking? Mu, right? That mu k value. So we can already start listing stuff. That's the coefficient of kinetic friction. What's 20 newtons here and what's 12 newtons here? What do they represent? Because they both have units of newtons, so you might think they're both forces, and they both are forces. But I need specific, subscripts for these forces. Joe, give me something.
12 newtons is force of 5.
Agreed. And what about the 20 newtons? What about the 20 newtons? It's the weight of the object. Remember, it says a student pushes a 20 Newton desk. Remember, when you describe an object, you can describe either its weight or its mass. Its weight or its mass. The mass units would be kilograms. Very good. Kilograms. So because the actual apparatus of the desk is given in newtons, it's the weight of the desk itself. Well done. The distance traveled here is 24 meters. That's given in the problem itself. So we have all the givens listed so far. Now we have to go to each section, part A, part B, part C. Part A says how much work is done by the student on the desk. Now, by the student on the desk, what force is utilized in this case or in this problem? What force? Is it the applied force? Is it gravity? And we haven't even listed friction yet. Or is it friction? Which of those 3 things, applied force, gravity, or friction, is a result of the student? Applied force. The student can only apply force. The student cannot produce friction, him or herself, on the object. I guess technically they could. Right? If the object were already moving, you would put your hand on top of it and slide under your hand, and that would be some friction. But in this case, it physically says the student pushes, right? The student pushes it. So the applied force is useful for the student part. So let's take a look at that. So we want the work done by the student. So I'm going to call it the work done by the applied force. But the problem here is I don't know what theta is. It's not given. It's not given in the problem. So I could draw a diagram to see this a little bit better, or I could just use logic in this problem and try to recognize or deduce it from the information given. What are we thinking here? If a student applies a horizontal force on a desk, and the desk is clearly moving which way? Horizontally. What would theta be in this case? 0 degrees. Theta would indeed be 0 degrees. So here's the desk. There's the applied force. And the direction of motion is the same as the applied force. So theta is indeed 0 degrees. And that's 1. Cosine of 0 is 1. So that's useful to recognize that it doesn't affect my answer, actually. The applied force was 12 newtons over a distance of 24 meters. I get an answer of 288 joules. Why is my answer positive? I'll give you 2 reasons here. Logical and mathematical. Why is my answer positive, Nick? Good. The angle is 0, or it's between 0 and 90. and therefore the work done is positive. So mathematically, because this angle is between 0 and 90, the answer has got to be a positive work. Logically, why is the answer positive? Logically. Not mathematically, but logically. Joe? Because what?
You moved it forward.
Okay, good. So he, instead of impeding motion, he aided motion, right? Or he aided motion instead of impeding motion. The minute you impede motion, what do I mean by impede? I mean resist motion, like friction. That's negative work logically. When you assist motion or aid the motion of the object by speeding it up or pushing it in the correct direction that it's moving, you're doing positive work. So there's a logical reason for work being positive, and there's a mathematical reason for work being positive. And the same goes for work being negative. So let's take a look at part B now. Part B says how much work is done by the floor on the desk. What force acts between the floor and the desk? Friction. So part B, although it doesn't say how much work is done by friction, that's what they're asking. So for those that struggle sometimes on these tests, where you have to actually dissect the problem, here's a great example. He nowhere says anything about the work done by friction. He doesn't ever say that anywhere in this problem. It tells you the coefficient of friction, that's it. It doesn't ask you what is the work done by friction. But part B inherently is asking that. How much work is done by the floor on the desk? And the floor is impeding the motion of the desk. The floor is doing negative work. So let's figure that out for part B now. So let's do part B over here. So the work done is going to be the force of friction times the distance times the cosine of the angle theta. So it's the exact same formula, but notice my F has a different subscript. I'm no longer looking at the work done by the student or the applied force, but now I'm looking at the work done by the frictional force, by the resistive force of the floor. What's my formula for force of friction from last chapter? Ff equals, it's on your formula sheet if you have to look, and that's fine if you need to. But this is a formula from last chapter. Ff equals. What is that formula? No, Mr. Mays? I saw the hand pop up for a sec. You sure? It is?
Is it mu FN?
It is mu Fn. Very good. So I'm going to replace Ff with mu Fn, and then I'm going to carry everything else down. So again, the force of friction is equal to mu Fn. That's why I said, last chapter might come up a little bit. This is where an example that comes up. It's mu times Fn. Well, in this case, it's kinetic friction, so I can call it mu k. Right? Mu k, it's kinetic friction, so I'll give a little subscript for the k there. But what is Fn now in this problem? What is Fn? Joe, what are you thinking?
Would it just be 20?
Why 20, Joe? You're right, Joe, but give me a logical reasoning.
Because it's the weight
Good.
of the desk, and that's how much force
Okay.
being pushed against the ground.
How come, Joe? What state are we in vertically? We're in a state of zero net force, right? Zero acceleration. Rest, equilibrium, right? Equilibrium. Vertically, fine, you got the idea. Vertically, we're seeing in this problem, look at the blue forces I drew on the diagram now. This is where a free body diagram could come into play. If I'm applying a force at an angle, well then part of that force is horizontal and part of it is vertical, and then I have to solve for Fn. I have to figure it out. But think about this logically for this example. The student is pushing this object horizontally like that. If I'm pushing horizontally, the weight pulling down has to be balanced by the normal force pushing up, because this object is not moving vertically. This object is not lifting off the ground. So vertically, we're in a state of equilibrium. So I could do all the math and say Fn minus Fg equals 0, and then solve. So what Joe is recognizing is that this is my vertical equation really right here. Right? That's what's happening. I've got the normal force pushing up, I've got the weight pulling down, that equals 0. But logically, just look at it. If these are equal to 0 when you subtract them, Fn has to be 20. Because if this is given as 20 in the problem, right? What minus 20 gives you 0? Well, only 20 minus 20 gives you 0. And again, we're in a state of equilibrium. So the normal force must be 20 newtons. So I could jot that down if I want, but I could also just directly plug into the formula now. 0.2 times 20, give me 1 second, times 24, times the cosine. Helen, what's the angle for friction? 180. Okay, the answer in this case will be a negative answer. It's going to be negative work done. It's going to be negative 96 joules. All right, so tonight, here's what I want you to do. Finish up part C. That's it for this, okay? You can do the regular homework, obviously, as normal. But look at part C for these notes. Regular homework is on the next slide. Okay, so make sure you take a look at this one.